Let us recap from the last lecture that we now have two differential equations that we can solve exactly. The first one is y prime equals ky, whose solutions are fairly straightforward and correspond to either unbounded growth or decay all the way down to zero. The second one, of the form y prime equals a minus by, corresponds to the growth or decay that has a horizontal asymptote that can be calculated out of the coefficients of the differential equation itself. In this class, we're going to see a couple of applications and how to apply our general formulas to particular cases. The first one is the organismal growth problem that we have seen previously. So let us remind ourselves that we stated that the mass of the cell is equal to density, which is a constant, times volume, which in the case of cubic cell is simply length of the side cubed. From here, we derived the formula for the rate of change of mass as 3dl squared times dl by dt. And we actually said that this 3 will get absorbed into the density constant, so we can simply have it as d here. Later, we also approached this derivation of this formula from a different angle, talking about how the cell ingests food at the rate proportional with the proportionality constant s to the surface area, and it consumes food at the rate proportional to the volume, so VL cubed. Now, when we are talking about the change of mass, we can think of that as absorption minus consumption. So what we have is SL squared minus VL cubed. But on the other hand, this is the same as what we derived using a different approach. So these two must be equal. Again, let me pause here for a second and remind you that the surface area of the cube, of course, is 6 little faces, but I am omitting 6 here because it can get absorbed in the proportionality constant s, the same way that 3 here can get absorbed into the density constant d. Okay, so the numbers get absorbed into the actual letter constants here. Now, setting these two equal, we can solve for dl by dt, and what we end up getting is, let me write this out slower. So SL squared minus VL cubed, which is the right-hand side here, and we will divide both sides by DL squared. So all over DL squared. And then after we have split up this fraction and canceled out the L's, we're going to get S over D minus V over DL, which we can rewrite in terms of constants, or we can simply sort of stand back a little bit and look at this equation carefully. What I have here is the derivative of L is equal to some constant minus some other constant times L. This is exactly of the form y prime equals to a minus by. So the great news is that before, this was the equation we did not know the solution to, but now we can, in fact, solve it. Now, I'm not going to write out the general solution formula for this particular application, but I encourage you for practice. What I will point out, however, that is important is that recall from the last slide, when we analyzed equations of this form, we have noticed that their solutions have either a steady state at a over b or a horizontal asymptote at a over b. So a over b is a number of interest. In this case, this corresponds to the horizontal asymptote of the solution as a over b. My a is s over d, my b is v over d. So we have s over d divided by v over d, or in the simplified form, s over v. That means that in my solution, I'm going to go from the derivative of L to L itself, and L itself as a horizontal asymptote will approach S over V. So as the cell grows, these constraints of the ingestion and the consumption of nutrients will lead to the length of the side of the cube of the cell, so the dimension of the cell to be bounded by this ratio S over V. So the ratio of the proportionality of the surface area to the proportionality of the volume. These two constants are what decide the limiting size of the cell that it can possibly approach as it grows. Let's take a look at another application, the Bertanallanfy equation, named after Ludwig von Bertalanffy, an Austrian biologist known for his work in biology as well as information theory. He is one of the founders of the general systems theory and is actually well known for this equation as the mathematical model of an organism's individual growth. So what we notice here is that this equation looks slightly different from the ones that we have seen before, but maybe it's just the exact same form disguised as something else. So if we are to solve it, let's try to massage it a little bit to see if it's of a familiar form. So what I have here is dl by dt, where L corresponds to some kind of a dimension, generally of an animal. If it's a spherical cell, this L will be the dimension that is the radius. If it is a cubic cell, this will be the size of the length, the side length. So what I have here is, notice that I have a K, a constant of growth. I have an L, which is the same as my dimension here, and I also have L infinity. This is what is called asymptotic length, and this is also a constant. Now, the reason it's called asymptotic length is going to become apparent later in the analysis. For now, we're simply treating this as a number. So what I'm going to do is open up the brackets and multiply Kn. So we have KL infinity minus KL. So here it's a constant times a constant, here it's a constant times my variable L. So this makes it very clear that this equation in fact is of the form A minus BY, because this is a constant, can be modeled by A, and this is a constant that can be modeled with B. This means that I can solve this equation. So let's write out the general solution. Recall that the general solution will be A over B, so in this case, KL infinity over K. Let's write this out in full detail. Minus A over B again, KL infinity over K, minus the initial condition. Here we're told that L naught is 0. So for example, in terms of length, a cell starts at some trivial dimension. So minus 0 e to the power of minus b, which is k, t. It's going to take a few times before you really get a hang of going from the general form in terms of AB to the constants, so do practice this a little bit. Now, I'm going to simplify this equation as best I can. So first of all, I notice that minus 0 I can simply ignore, and I can also notice that in all of these terms, k's will cancel. So in the end, my equation is actually going to look quite simple. It's going to be L infinity minus L infinity e to the minus kt. As already pointed out previously, A over B is an interesting quantity when it comes to these models because it describes the horizontal asymptote. And here I can see that A over B in fact turns out to be equal to simply L infinity. So L infinity is my horizontal asymptote for this model. There's another way to derive it simply from the equation itself, and that is to look at this equation and think of what happens as time goes off to infinity. So as t goes to infinity, this power becomes a very large negative number, minus infinity. E to the negative infinity tends towards 0, which means that this entire term tends towards 0, and all I have left is that L tends to L infinity. If we are to sketch this now as a graph, again, I'm only interested really in the positive values for t. I notice that my L infinity here is then my horizontal asymptote. In this case, it's known as L infinity. In the previous slide, it was also known as A over B. So I have this as a horizontal asymptote for my model, and my initial condition says I'm going to start at 0. Now I'm going to make an assumption that this is going to be a nice continuous curve, so it's going to approach a horizontal asymptote in some kind of continuous manner. Now I don't actually know whether it's a curve that looks like this or maybe a curve that looks like this. I'm just going to draw a general shape simply indicating two important pieces of information. It starts off at 0 and it ends up approaching or plateauing at L infinity. As I mentioned, this model is used for description of various animal individual growths, and in particular, this is one of the models that is used to describe fish length growth. Now, different species of fish, of course, will grow differently depending on their genetic makeup, and this is what the constants k and L infinity will actually help determine. But the general growth model is the same for many of the species. Let's just take a second here and really compare this form of the equation with the form that we have originally derived our solution for. Both of them have their advantages and disadvantages. The original form has the advantage that it's easily seen to be a constant minus a proportionality constant times the original variable, but this form has the advantage, after k has been factored out, of seeing the horizontal asymptote immediately. Both of these equations are completely analogous in terms of what solution corresponds to them. They're simply written out differently to highlight different pieces of information. This shows that it's a linear model. This shows the horizontal asymptote explicitly. Another application where we see the now familiar differential equation is Newton's law of cooling. Now this is revisited because you must have seen this in your Calculus 1 class, but probably under a different kind of setup. So let's start from the beginning as how Newton's law of cooling is actually stated and what that means for our solutions. The way it's stated says the rate of change of temperature, so this immediately suggests the derivative if we are to write it out. The rate of change of temperature is proportional, with some proportionality constant k, to the difference between the temperature of the object itself and the ambient temperature. So what we have is it's proportional to the difference, and it can go either way. The ambient temperature minus the temperature of the object, or it could be the temperature of the object minus the ambient temperature itself. Because the law of cooling is generally stated as the law of cooling and not the law of heating, we are mostly going to work with the first form, but the second form is completely analogous. It's simply going to depend on whether you want your k to be positive in one case or negative in the other. Again, because the law is stated as a law of cooling, it is the cooling case where we consider k to be positive, because the temperature of the object is going to be cooling down to the temperature of the ambient environment. If the object is heating up, in our model, this will correspond to k being negative. So we have here the same exact setup we have just seen with the von Bertalanffy model, where I have a constant k, another constant e, and then my actual object's temperature. So I can open up the brackets and rewrite it to see the a minus by form, or based on our previous analysis here, we know that this constant up in front actually corresponds to the asymptotic or the plateau length. So this here will correspond to the temperature that will eventually be reached by the object. And here we have, both intuitively and really from the mathematics we've just seen, the two cases. It can be heating up or it could be cooling down. So let's sketch two quick graphs of both of those scenarios. So if my object is cooling down, that means that it is starting at some initial temperature T naught that is above the eventual ambient temperature, and its temperature is reaching the ambient temperature slowly this way. If my object is heating up, that means that it's starting at the temperature that is below the ambient temperature E and is reaching that temperature slowly. So the two scenarios, for example, that we think about all the time is cooling down, the ambient temperature is the room temperature, and the object we're talking about is, for example, a cake being taken out of the oven. Heating up, we're thinking of the ambient temperature still being room temperature, but the object is, for example, ice that has been taken out of the cooler. Now again, because this is the form that we are familiar with, we can actually find the exact solution to the equation. So instead of talking about the rate of change of temperature, derive a formula for the temperature itself. Let's see how we can do it. We can actually do it in a number of different ways. We can do it from scratch, or we can do it from using the formula. Normally, once we've derived the formula, we will always use the formula, but I will take this opportunity to just practice the from scratch technique one more time to show you the actual algebra behind it. So my equation is t prime from the previous slide, dt by dt is k e minus t. And what I'm going to do, if you recall, is I'm going to want to rewrite this fully in terms of one variable that I'm going to call z. So here, z is equal to e minus t, and then I'm going to take a derivative of this equation. So z prime ends up being what? The derivative of e, which is a constant, is 0, and the derivative of t is simply t prime. So this is z prime equals negative t prime. I'm now going to plug all of this back into my equation, and what do I get? T prime is then negative z prime equals to, and on the right hand side I have k times z. I can multiply both sides by -1, and I end up with the equation that I definitely know the simple solution for. This is of the form y prime equals ky, except for, of course, y is being called z, and there is a negative in front of it. So the solution to this is going to be z equals to some initial value z naught e to power minus kt. Once I have a solution in terms of z, I would like to bring it back to the solution in terms of my original variable, which is t, and I'm going to use this relationship between the two variables to rewrite my current solution in terms of t. So z on the left-hand side is simply e minus t. Z naught is going to be e minus t naught, and I have e to the power of minus kt. If I now take a minute to rewrite the whole thing for t, because this is the temperature that I'm after, I'm going to move e to the right-hand side and then multiply everything by -1 to get rid of this negative. I'm going to get that t is equal to e plus e minus t naught e to the power of minus kt. And this is likely the form that you have seen the Newton's law of cooling presented in Calculus 1 courses. The temperature of the object has this relationship to the ambient temperature and some kind of cooling down constant K. Again, this is the way to solve it completely from scratch, but we really don't have to do this once we have derived the general formula. We can massage this equation in the same way that we've done with von Bertanallanfy model to match what we already know. So from the formula, from y prime, let's be a little more precise. From this formula, what do we have? So my original equation is of this form, so let me rewrite that. T prime is equal to k e minus t, which doesn't quite match the a minus by form, but in order for me to do that, all I have to do is simply open up the brackets here. So what I have is t prime is ke minus kt, and now I can notice that this will act as a and this will act as b, therefore producing the solution of a over b, so ke over k minus a over b one more time, so ke minus over k minus the initial condition t naught, which in this case we cannot assume to be 0. We have not been told to assume anything like that, e to the power of minus kt. And as before, let me just cancel things out here and simplify this equation a little bit. So what are we going to have? T is equal to e minus t naught e to the power minus KT. Okay, and these, I just noticed I made a small typo here. There we go, minus. And this is now the exact same equation as the one derived using the from scratch method. So of course the methods are exactly the same because this general formula was derived exactly through the substitution of z, and therefore the answers should be the same. Now once we have the general formula, we can use it to our advantage in a variety of applications, in particular any applications that involve cooling down and heating up objects that call for Newton's law of cooling. In the next application, you're going to see the approach that most of you probably have seen in first-year calculus and a slightly different way to write this formula down. I wanted to show you a little bit more of a variety of how this formula can be written, and in particular if the constant is not assumed to be negative and if the terms are labeled differently. For example, E often is labeled TA as the ambient temperature, and sometimes the terms here occur in a different order. So be mindful of the fact that Newton's law of cooling is what is described by the general differential equation, but can happen to be written in either of the format with anything to be assumed of the actual constant K. This doesn't mean that the Newton's law of cooling itself is changing, but the way that it's presented in the final formula might look slightly different, and you have to be comfortable with dealing with flexibly with the same exact law written in slightly different formats. One of the coolest applications that one can think of in terms of cooling down objects is how a blacksmith actually tempers the metal and then cools it down before they can temper it some more. So let's take a look at how a farrier works on a horseshoe. In order for that, let's first of all take a look at what does that actually mean? What does the farrier's job actually involve?
The goal of the unit is always the horse, and the horse is the most important priority that we have.
I'm just going to take the shoe off my crease nail pullers.
And without the horses, we wouldn't be a mounted unit. So everything that we do here is for the benefit of the horse.
My little friend, how are you? I often try to talk to these animals because, like anything else, when you're having anything done, it's always easier to get done when you're talking to something or someone.
The mounted unit was established in 1858. We're the oldest and largest mounted unit in North America. There's a very special relationship between a mounted police officer and the public. We have 4 facilities spread throughout the city. We have over 100 officers, over 50 horses, and 3 full-time department horseshoers on staff. They're here every day.
That's really the goal of the farrier. We try to keep the horse in service and comfortable and safe. Because believe it or not, it is 2,000 pounds of dead weight on top of 4 tiny feet. But I've been shoeing this horse for almost 10 years straight, and he knows me, I know him. And that's really the goal of the farrier. We try to keep the horse in service and comfortable and safe. It is a dream job. It's not even a job, really. We're kind of spoiled. What's up, Hanson? You all right, man? I know.
So as you saw in the video, the farrier actually molds the horseshoe to the horse, which means that he or she has to constantly work on the shoe until it reaches the right shape. So once they are working on it, they have to, before putting it on, cool it down to a temperature where the horse will be comfortable at. And this is what this question is about. The question says that while the horseshoer is working on the horseshoe, the actual metal is heated up to 400 degrees Celsius to be, in fact, Mendy enough. And then they dunk it in 25-degree or room temperature water. The water around the horseshoe stops boiling in about 30 seconds, and the horseshoe is safe to put on the horse when it's at approximately 60 degrees Celsius. What we're wondering is, when does that happen? So how long should a farrier keep the horseshoe in the water for it to cool down to the temperature that the horse will find comfortable to be put on? Okay, so this is our Newton's law of cooling. This is just a general formula from the previous slide, and let's fill all the information in that we have in this question. So the left-hand side here will be the temperature of the horseshoe. TA, the ambient temperature. Of course, the horseshoe gets dunked into the water, so the ambient temperature corresponds to the water temperature, which in this case is 25 degrees Celsius in both cases here. And then T naught is the initial temperature of the horseshoe. While the Fourier is working, it's 400 degrees Celsius, so this is 400 degrees. The one unknown is still the cooling constant, and that is something that we're going to have to solve for using other information provided in the question. Now, before we do that, let's put together what we have so far. So I have 25 plus, and then this is going to be 400 minus 25, which is 375 e to power k t. So this is my best model so far. Still don't know k, but I have all of the other constants in place. So the other piece of information we have not used yet is the fact that the water around the horseshoe stops boiling in 30 seconds. I know that the boiling point of the water is 100 degrees Celsius, so it's safe to assume that in 30 seconds, the temperature of the water around the shoe is 99 degrees Celsius. So let's record that. In 30 seconds, the temperature, in 30 seconds is 99 degrees Celsius. Now, instead of writing it this way, we're going to write it inside our model. So the temperature is 99 degrees at the time of 30 seconds. Okay, so just matching the model to what I have, replacing the time with 30 and replacing the left-hand side with my actual temperature, I have an equation like this. The only constant here is k, and we can easily solve for that. I'm going to skip the steps, but you should get the number that is approximately minus 0.0541. This is a really good time to stop and make sure that you're on track in terms of constant. The cooling constant has to be negative in this case, which it is, so it seems like at least our algebra is working out okay. Now the question is, when can the farrier put on the horseshoe? And that is when the temperature is at 60 degrees Celsius. So what we want to know is, for what time t is the temperature equal to 60 degrees Celsius? And once again, we're going to take it through the model here. So the temperature on the left-hand side here has to be 60 degrees for the horse to be comfortable, and the right-hand side is here. Now I know my constant k, and I will be after the value for the time t on the right-hand side. Okay, so altogether, the equation I have is 60 is equal to 25 plus 375 e to power k, which we've just discovered was 0.0541 times t. Once again, this equation simply has one unknown, which is t, and we can solve for it. I'm also going to skip the steps here, and t will work out to be approximately 43.8. This is time. Be careful in units, it says seconds here, so our time all along was in seconds. So the horseshoe will be cool enough, cool down to 60 degrees Celsius, and therefore be able to put on the horse in 43.8 seconds. Please make sure you actually go through these simplifications and solve for these values, just to make sure you have enough practice solving exponential and logarithmic equations here. One word of caution is, it's easiest to solve these equations if you first isolate the term that has the constant in it. So do not apply logarithms to both sides until you have the e to whatever power completely isolated. So move, let's say, 25 over to the left here, then divide everything by 375, and then apply logarithms. Make sure you go through this, because there will be more problems like these in class and, of course, on tests.